Pleasure to introduce Ivan Smalyukh from CU Boulder, who will tell us about nematic colloidal matters. Ivan.
Thank you so much. It's a great pleasure to be here, and thank you for the opportunity to present about our research. Today, I'll discuss with you the nematic colloidal motors that are powered by light. And this work was done mainly by my students and postdocs, Ye Yuan, Chinkun Liu, former postdoc, Bogdan Smalyukh, and also an undergraduate student, Ganima, whom you see here. So I'll start with a brief introduction as a motivation to colloids in general. So we all know that Einstein himself, when he was working on his PhD, he was explaining Brownian motion over colloidal particles. And in doing that, he also was proving that atoms and molecules exist, and he was deriving from very basic principles the size of these building blocks of matter, right? So it's quite amazing, and out of his 1905 three famous papers, only this one was part of his PhD thesis, right? So in some way he was a soft matter scientist by training, we could claim it. But of course, this work introduced the entire colloidal atom paradigm. And so for decades after this, people have been realizing different types of colloidal crystals. They were demonstrating that indeed there is a lot in common in the behavior of atomic and molecular crystals and these colloidal crystals, where we can have similar types of defect dynamics, melting, crystallization, glass formation, and so on. And so it became especially interesting to bring this paradigm even further when recently chemists learned how to synthesize all kinds of very interesting nanoparticles. So for example, gold nanoparticles that can give you properties extremely different from bulk gold because of surface plasma resonances. So you can even have those different colors because of the resonances at different frequencies as you tune the size and shapes of these particles. We also know about quantum dots, where again you can kind of tune their behavior and make them behave largely like artificial bigger atoms. And so you could think about making new materials that would benefit from the properties of these nanoparticles that are very different from properties of bulk materials, right? Yet you would need to assemble them into some structures in a very controlled way, like it happens in nature with atoms and molecules. And so unfortunately over decades it was very difficult to go beyond the high symmetry colloidal crystals like these cubic lattices you see here. And so on the other hand, not so long ago, a very new type, a different type of colloidal systems was introduced, where instead of isotropic fluid host, we would have liquid crystal, nematic fluid, and of course the building blocks, the molecules, are much smaller than the colloidal particles that you put in. But that allows you to control the surface boundary conditions on these particles to be perpendicular, tangential, or even conically degenerate. So you can, with that, define a lot of different types of behavior. And so with just right control, you put nanoparticles and you see them crystallizing in liquid crystal into the lowest symmetry possible triclinic colloidal crystals, as for example in this our work in the past. And moreover, again, like in atomic and molecular systems, you can reproduce these behaviors of melting and crystallization by, for example, probing the Lindelman parameter. And also what's amazing is that you can achieve this behavior at filling factors that are only 1% or so, or even under 1%. Right, where the volume taken by particles themselves is extremely tiny because the interactions are rather long range in this case. And so why do we have all of this large diversity of behavior and richness and anisotropy in interactions and ability of forming these types of low symmetry crystals? Well, it's just because we have that control of molecular alignment around the particles, right? So in here there are some very common types of nematic colloids where we have Saturn defects, ring defect, or point defects, bourgeons, and as Micha Ravnik already very nicely discussed with us a couple of days ago in his lecture, these are very analogous to electrostatic charge distributions, right? Because as you would look at the tilting of director around these particles, and for example, if you were to plot on some surface surround this particle the x component perpendicular to far field director component of the director field, you would have this kind of negative and positive signs of this x component alternating around these quadrupolar colloidal particles in a very similar way to what you would have in the case of charge distributions, quadrupolar charge distributions on spheres, right, in electrostatics, where you would describe these distributions with this expression in here. And we already know from Micha's lecture that this is because the Frank free energy minimization gives us Euler-Lagrange equation, which is of Laplace's type, and then expansion of the solution into multiple series allows us to bring about these analogies. But not only we can have dipoles and quadrupoles like in these cases in here, we can also have hexadecapoles where the tilting of director or the sign of x component of director is changing within each quadrant, and that is analogous to a charge distribution corresponding to electrostatic hexadecapole, as in this case in here. And so this brings about richness of behavior, because it's not only in terms of this distribution of director distortion around the particles, but also in terms of interactions we can bring analogies with electrostatics, right, where expressions are quite similar because we invoke the multiple expansions in here, but also with hybridization of atoms, and that makes it very interesting from the standpoint of view of colloidal atom paradigm. So for example, for these hexadecapoles I was showing you, electrostatics would predict we would have this type of behavior, as we would look at the dependence of interactions as a function of orientation of separation vector versus the far field director. And so you would have then 8 sectors of repulsion and 8 sectors of attraction, very rich behavior. You take laser tweezers, you hold 2 such particles, and indeed you can see that particles attract and repel in these corresponding 8 different sectors, as you can see in here shown for us with the help of the color-coded trajectories of the 2 particles as they interact when we release them from laser tweezers. Well, so this is all very interesting because in some way this periodic table did not change much over the last 100 years or so, right? Remember, the last element that was introduced was this number 118 about 2 or 3 years ago. So reminding you that in all of the elements in this periodic table, we only have in the ground states filled orbitals SPDF, right? So far, there are no elements that would have these g orbitals. That would be actually the next row that would be starting from element number 121. Right now, if you look at this other colloidal atom, the big atom, right, it does have the structure that would correspond to the G shell of colloidal atoms. So in here, of course, we don't have wave function, but electron wave function, but we do have what we could call director-Wiggle wave function. And so the common thing between these colloids and these atoms is that we use the same mathematical language of the spherical harmonics, and so that again makes it very interesting. So now, as Micha was showing us already, we can have all kinds of multiples, and and these are just examples of a very big zoo of colloids that we can realize. And so for example, for hexadecaples, for different values of m, we can have all of these different types of structures that can have different interesting interactions and therefore self-assembly into colloidal crystals. But we are missing something, and something very basic. So so far, we did not have monopoles. And for monopoles, you would have director tilting in one direction, right? So you can see for dipoles and quadrupoles, the director tilting is changing around, right? For dipoles, as you can see, you have two opposite tilts. And so this is what I'll start my discussion today from. And so the idea is that the colloidal particles we put in liquid crystals are analogous in some way to the nucleus, right, of the real atoms, right, and the director distortion around them in some way to the wave function. And so for us to have an analog of a hydrogen, right, we would need to have the director around the particle tilting in just one direction. Now, you immediately realize a problem with that, because to minimize elastic free energy, that distortion should relax to a uniform state, right? And so that was part of the problem why such colloids could not be easily realized for a long time. Now, what I'll discuss with you today is how we use optical torque to balance such elastic torque and therefore realize elastic monopoles. And so in this case, we will use azobenzene dye molecules that are highly responsive to light. And in liquid crystals, including liquid crystal industry, these type of azobenzene molecules have been used for a while to align liquid crystals on surfaces, because as we shine linearly polarized light on this surface, then these azobenzene moieties will align perpendicular to linear polarization of light. And so that allows them to align liquid crystal molecules parallel to azobenzene molecules, and with light you can control that alignment. Now, what's very interesting is that as we were playing with this alignment layer some time ago with my student Angel Martinez, he observed these kind of beautiful patterns as he was shining polarized light through liquid crystal. And that was unexpected, and it took us a while to understand what was going on. But effectively, what we have is some effect of birefringent medium, right, that causes coupling between polarization of light that passes through liquid crystal and that response of azobenzene monolayer, and then that gives rise to these different beautiful pattern formations that at that time we could explain in more details. But what we wanted to do now was to apply these principles to colloidal particles. And so we can fabricate colloidal particles in different types of shapes and sizes. And so in here you can see colloidal platelets that we produced for this purpose. They are half a micrometer in thickness and just a couple micrometers in lateral dimension, so even smaller. We can graft this type of azobenzene unit containing molecules on the surface of particles, put them in liquid crystal, and then use light to control the alignment on the surface. And so what's very interesting is that the response is amazing. You only need under a nanowatt of light to have very strong response. And so this now can cause symmetry breaking, and so by balancing optical and elastic torques as we rotate these particles, we can induce elastic monopoles. And indeed, in here you can see them. I hope lights could be dimmed a little bit because it's a bit hard to see some of these. And so is there a way to dim light? Right, so you can see in here, as we observe them between parallel polarizers in a microscope, these particles rotated in two different directions would have different appearance, and then with the help of polarimetry in the microscopic setting, we can also probe the polarization ellipses of light on the pixel by pixel basis as it passes through a liquid crystal with such a microparticle within it. And indeed, we can see that these particles rotated in two opposite directions as we control polarization of light. When the polarization of incident light is parallel to far-field director, those two states can occur with equal probability, but as we rotate that polarization away, we can control which of these two elastic monopoles we can obtain. And so indeed in here, around the particle, we have monopole type of distortions. Now it's important for us to be able to control the structure of these multiples, but also to be able to image them. And you don't want the two processes interfere with each other, because I told you the system is extremely responsive to light. So however, we can use blue light to excite the dye molecules, and we can use red light for imaging, because you can see from this graph in here that the azobenzene molecules we use have very little response to red light and very strong response to blue light. And you can see from this video how in situ in a microscope we can observe with red light the response of these particles to blue lights with different polarizations in here. And so in this setting where we have two channels of blue light of excitation and red light imaging, we can probe the structure and also control it with light at the same time. So now it's important to understand that the director distortions are in both lateral and axial directions. So as you go in direction perpendicular to the platelet, in here up and down, and also in lateral dimensions, you can see director is everywhere rotated in the same direction, and this distortion decays. So you could define some sort of three-dimensional volume within which you distort this director field in a single rotated direction. Now, as you rotate it into opposite directions, you then have effectively two monopoles of this type. Now, what's very interesting is Dejean and Brochard, again employing electrostatic analogy at some point, were able to predict what would be the elastic torque if you were to rotate director with some particle like a grain of magnet or something like this in a certain direction. And so this was their prediction that in small angle case, it actually this elastic torque scales linearly with the maximum angle of rotation that you would have. And so this is elastic torque, and then it can be balanced with optical torque that again we can control by using polarized light of different intensities. Now in very simple modeling, we can consider what happens if we rotate director somewhere within the sample and then relax it within a large three-dimensional volume. Indeed, we can see that as we fit this x component of director, the strongest moment in the multiple series is the monopole moment. So we do indeed have elastic monopoles in this case. And so what we have essentially is a new animal in the zoo of multiples, right? So before we had dipoles and examples of quadruples, and you can see how director tilting is changing around these particles. The particle that I was just discussing with you at no excitation, or when excitation of polarization of light is perpendicular to far-field background, is also a quadrupole. However, as we shine light, the blue excitation light, with some polarization state that's different from being perpendicular to far-field director, then we have the excited monopole state, right? So in some way we have monopole as an excited state, but we also can have it living even after you turn off light for a relatively long time. Moreover, which can be thousands of seconds. So in that way, you can probe interactions between these colloidal atoms in the excited state. So as we control polarization state, we can switch them between also almost instantaneously within milliseconds to quadrupole state or back to monopole state, and monopoles of different sign as well. So what's very interesting is also how these particles diffuse around. We all know that regular colloidal nematic particles, dipoles and quadrupoles, have anisotropic diffusion in liquid crystal. So if you probe diffusion coefficient as a function of these different angular directions, you would see this kind of angular dependence, right? And different diffusion coefficients in directions parallel and perpendicular to director. But when you have the monopole, it's not only that. Actually, this anisotropic characteristic angular dependence is not aligned with the far-field director, as you can see in here. So they are diffusing in a very asymmetric way. Moreover, what we can do is we can probe the elastic interactions between these particles using laser tweezers as we release them from laser tweezers. And what we see is that the particles with the same signs of elastic monopoles always attract in all angular directions. That's different from electrostatics, right? We'll discuss why that's the case, where like charges repel, of course. Well, also as we probe separation distance versus time, and also potential and force versus distance, we see them scaling exactly as you would expect for multiples. In a similar way, as we have the elastic multiples of opposite signs, they always repel up to distance where these interactions become comparable to thermal energy, and the distance and potential and force dependencies also scale as you would expect for these multiples. Moreover, you can switch the sign of these multiples, which kind of is counterintuitive. You can switch signs of charges, right? Cannot do it in electrostatics, at least not me. But in here, we can do that. And so you can see in here, this is a movie where we are actually switching at some point, right? And so I encourage you to watch it. But in here, the details, so originally we have them of opposite signs because we shine light on two particles with different polarizations. They have these distortions. They repel in this case because as they repel, they can minimize the energy of distortions between them. Now, as we switch the sign to like charges, they start attracting because then they can minimize this elastic energy. And so differently from electrostatics, like charges attract, opposite charges repel in here. Now you can see how exactly that happens as we change polarization in here, and you see that the repulsion is changing to attraction. And so again, all is similar to electrostatics, but just the signs are opposite of interactions. Now, as you increase intensity of light a little bit, what you can observe, and I hope you can see in here, is that these particles start spinning, not only just being tilted away from some orientation, and as they interact and attract and self-assemble, they continue to spinning, to do spinning. And so again, for this case, we can analyze the distance versus time, and also potential versus distance. And what we see is that in this case, when they are fully spinning, they don't interact as monopoles would. But that we can understand actually because you can see in here the spinning rate is much faster than the time scale of the interaction. And so within that time scale, they rotated many, many times. Again, I hope you can see this video. And so for that reason, the signs of the monopoles are changing from positive to negative all the time, and their effects are canceling out. So as a result, we have quadrupole-like interaction between them, and indeed it's similar to what you have for the very same particle as you switch it to the quadrupole state. What this means is that we now have an interesting outer equilibrium behavior, and as we go to somewhat larger intensities, and I'm talking about 2 nanowatts only, right? In this case, we can have these particles spinning continuously, right? And so you can see this happening here for this polarization of excitation light under different orientations of polarizers. And so we can understand what happens in here because liquid crystals has the interesting optical properties as it interacts with polarized light, as we know well from display applications, right? And so as light of certain polarization, like this one in here, is coming in, then as it passes through, it makes the azobenzene molecules rotate, but as they rotate and torque director as well, at some moment you have enough of director distortion to change that polarization state of light, and that causes more rotation, and under some conditions you can develop a feedback mechanism that allows you to produce this continuous spinning of the particles, right? And so that behavior is very rich. You can see it's always when blue light is shining on. I must say that it's a very simple blue light. You could filter the light of this room and spin those particles. It's enough intensity. It's not structured, not laser light, right? As you turn it on, you can see particles spinning. Turn it off, it's not spinning, right? And so
what breaks the symmetry of which way it spins?
So it can be spontaneous when your polarization is parallel to far field director. U is equal probability one or the other. But if you rotate that polarization a little bit in one direction, then that coincides with the direction in which it will spin. So then there is coupling through optics.
Is the local structure chiral?
You will have a twisting and untwisting, but as light comes from one side, it will be twisting to the one direction.
Because there is a vectorial asymmetry in the direction of the light coming in, that combined object has chiral.
Yeah.
I see.
Well, right, on one side of it, but on the other side it will twist back to meet the far field uniform background. And so also what you notice is that the frequency of spinning has this type of dependence, right, on the power of the incident light. It increases with this power, but there is some threshold on the order of 1-2 nanowatts in here, and that depends on polarization of incident light and other conditions, and later on we will understand where this type of dependence, square root dependence type comes from. In a little bit I'll discuss that. But importantly, we can reproduce this type of dependence with the threshold as we increase intensity of light and then decrease it as well. And so what's also interesting is that you probably notice there are some little bosoms at the vertices, and these bosoms under some conditions would be sticking and sleeping at the vertices. And so we can probe what actually happens during all of these stages, because we can do video microscopy with polarimetric capability at the same time. So as you're taking this type of images and you do it for different polarization states of incident light, then you can recover the azimuth and ellipticity. Ellipticity is plotted here with the colors of the polarization ellipse as light passes through, and that gives us insights into what happens with the interaction of light with a system. We can model it using the Jones matrix method, and this our polarimetric characterization is consistent with the modeling as well. But zooming into more details of the structure of this rotation, as we have with time, you can see that for different intensities of light in here, the angular speed is not a constant, right? It has quite a lot of structure. And so as you take one period in here, you will see that there are a lot of peaks, you know, maxima and minima. Now, as you would take a lot of these images, you would realize that the spinning is the speed is the slowest when you have your bosoms pinned to the vertex and rotated to some angle, maximum angle, before it sleeps. After it sleeps, the speed becomes the fastest, and so on, right? So this rich behavior we can correlate with the sticking and sleeping of the bosoms on the vertices of these types of particles. Now, what's important is that we can use different states of, in this case, linearly polarized light at different orientations with respect to the far-field director, and then as we initiate this dynamic state, we can further change that polarization state, and with that we can control frequency of spinning, and so as you can see this being done in here, and moreover, what is also very interesting is that we can see rich behavior in terms of development of the textures, you know, as they are spinning over a very long time, right? So in the beginning, as you just start spinning, you oftentimes have these multiple domains because the little azobenzene molecules have tilted in different directions, a little bit to different directions, but with time these domains coarsen, and then you start getting these types of more uniform textures, as you can see in here, and that also correlates with the frequency of spinning as well. And so you can see in here also that you can control these dynamic states with polarization states. So in some cases you have bosoms that are sticking and sleeping. In the other case you have you know, something different which looks a lot like you know, some form of a domain wall where the director is changing slightly differently, and you can see there's all different patterns, and they correlate with how the particles rotate. Now, not only we can design the uniform rotation, but also different types of oscillations, and so you can see from the examples of these videos in here, I hope they are running, that we can make them oscillating. This is actually in white light, so you don't need to have only blue light. It's okay to use white light as well. And in the case of oscillation, the frequency dependence is linear. It's different from the continuous spinning we saw before. Now, importantly, we can also design different types of shapes, like, for example, cogwheel-like, or you could self-assemble many different types of particles, and then the you know, spinning becomes even richer because you then have these all geometric features interacting with the alignment of the background liquid crystal, and so you can see that the angular speed can be designed and controlled that way. So now, remember, I told you that at some moment we'll discuss why we have this type of threshold and square root type of dependence in our case, right? Well, so the optical power is dissipated into two things. One is the rotation of this platelet in the viscoelastic medium. The other one is the director distortion that is also being generated and relaxing all the time. So director is dynamic. It's not in any way static, right? And so you have then these two different contributions, and so you can see that this is balanced optical power is balanced with this two types of mechanical power output, and this explains why we have square root type of dependence of frequency on the optical power in here. Now, what's very interesting is to ask a question, how efficient these light-powered motors are. Well, the output, if you divide output and input and multiply by 100%, you know, at some 200 nanowatt, we can get fairly good efficiency, which is kind of sounding modest, on the order of 10 to the power minus 3%, not so efficient, you would say, but you would be amazed that this is still by far the most efficient light-powered colloidal motor so far, because the ones demonstrated before us were in the range of 10 to the power minus 12, minus 8, right? So this is already 5 orders of magnitude improvement, but there is more to design, you know, I would say, because we did not really optimize too many things so far. We just played with it. Also what's very important to note is that the threshold intensity that you need in here is lower than the ambient light intensity. So as we have these samples anywhere in our hands, these particles are spinning there, right? And so that makes it very interesting too, because you don't need some high power lasers and structured light or so on. Also what's interesting is that we can translate the rotational motion into, or oscillating motion into translation as well. So for example, one simple way to do it is just to use thicker particles, right? That would be like a micron in thickness, and then we can make them also translate, because the particles tilt a little bit with respect to the plane containing this far-field director and parallel to the cell substrates, and then as they are oscillating, they're also translating, as you can see in here. Moreover, you can also design the particles that are oscillating, you know, and also in this case, because of the effect of the azobenzene molecules on the edge surfaces that also respond to light, you have non-reciprocal response, and that allows you to have these particles translating as well. Well, of course, this all so far was done at a level of a single particle or couple particles, and the question is, how do we scale them from 1 to millions, and perhaps to composite soft matter systems? And so in here you can see nanoplatelets that are under 10 nanometers in thickness, but 2 micrometers or so in lateral dimensions that we synthesize in very large quantities with wet chemistry approach, hydrothermal synthesis. Then these platelets can be coated with silica, and then again, that's just like a nanometer or 2, and then they can be further functionalized with azobenzene dyes, and then we can put them into liquid crystal containing these molecules like 5CB that you see in here. And then these platelets align parallel with their large area faces to the far-field background. And the high concentrations, they can even exhibit their own directionality of ordering that would correspond to the ordering of the normals to these platelet surfaces. So that way you can get also different types of biaxial hybrid liquid crystal behavior as well. But then as you make such particles in large quantities, and then here you can see them being functionalized with the azobenzene, and you can see that azobenzene attached to these particles, because as you spin them in the solvent, that color stays with the particles, and then they can be redispersed in a liquid crystal, and they give the rise to collective behavior, about which I cannot talk much because this is very fresh and still needs to be studied in details. This brings me to the conclusions. I hope I was able to show you that we have developed elastic colloidal monopoles that can be switched by light, both between the opposite signs, and also the strengths can be controlled, and they can be switched to quadruples. They are different from electrostatic counterparts in that the like charges attract and opposite charges repel. I also showed you that we have light-powered colloidal motors, in terms of efficiency, we feel there is a lot of room for the design, because these biological motors, which for many of us are really true marvels of nature, they can have nearly 100% efficiency, this flagellum motor, right? Despite being truly nanoscopic in dimensions, and it's amazing that in the course of evolution something so amazing happened, right? Well, so far we did not have millions of years of evolution. We just started this project, but we do believe that there is a lot of room for designing these types of systems, making them much more efficient. And although it will be hard to compete, but we certainly can improve the efficiency of these optical motors. And I think this is synergistic with the topic of this program and this workshop. There is a room for designing self-assembled motors and machines in colloidal liquid crystal matter. Thank you for your attention, and before we conclude, I just want to remind you about the conference we have. It's going to be one of the bigger liquid crystal conferences, already 165 participants, and looks like we'll have even more. So we hope to see you there as well. Thank you.
So first, this is really beautiful. I was wondering an obvious thing. The gap between the ground state and the, what I guess you're pumping the pi star in the blue, is about 50 kilocalories per mole, if I remember. So this energy has to be released somewhere. Don't you get local heating around the particle? And isn't it worrying when you have the million particles?
Right. It's a very low power that you dissipate somewhere. So you don't have, the heating that, would cause transition to isotropic phase, but maybe some, little change in viscosity or something like this. But this is part of emergent response, if you wish. Those systems in general are quite complex, right? More complex than pure liquid crystals, where you have a single component medium, and when you put nanoparticles with ligands, with all of these parts of the design, more complex behavior, but still we can understand it, right? So yeah, but the heating is not substantial, I would say.
For the nanoparticles, how fast do they rotate?
They can, it's somewhere close to 10 hertz, so they are not super fast. I think there are, again, there might be room for optimizing, but, that's where we are so far. And, like some of these results I was showing in the very end, they're really in progress, so my students warned me not to talk much about them.
If you have two of these modulated rotating particles, do the changes in frequency as you rotate affect their interaction in any way?
Absolutely, yeah. And so in the example I was showing, they were uncorrelated, right? So they were spinning at different frequencies, and that's part of the reason why the monopole contributions canceled out. But we could design differently, and so there is again a lot of room for playing with those systems.
Okay, well, let's thank Ivan again for a great talk.